some pretty easy stuff today. Are you guys into your decimals already?
Mm-hmm.
19, 2 3/4. What up? I'm not sure about her. She's white.
Okay, so you're in here, right?
She's
Mm-hmm.
I'm not up here. Let's just.
All right, we'll be using this here a
here
little
I
bit.
am.
One thing I think I want you to do here today is this. In your decimals to start here today, I want you to go up here to the settings. Okay?
Settings.
Mm-hmm. Make sure radians is picked for you. Okay?
Projector mode too.
But I'm 26 in 3A.
26 on 3. Does that mean you'll make it?
Are we good here?
Yep.
Number 1 and 2.
Okay. So make sure you're in radians up there. So let's get rolling on the notes here. It's pretty easy here. Hey guys, we're going to start looking at graphs and trig functions, and not going to get so much consumed about what it is that they come up with. But guys, you might want your special angles chart as well. You guys remember the one that we've been using an awful lot this year?
Yeah.
Want that special angles chart to help you with this here, guys. And our job today is to understand the graphs of the sine function, cosine function, tangent function, cosecant, secant, and cotangent. Okay. Right here it says each graph can be derived from the unit circle, so that's where that special angles chart comes into play. And it also can be derived from the idea that the tangent function is really equal to what here, guys? What's it say in the notes?
Sine over cosine.
Okay, don't forget this. Sine over cosine is considered your tangent function. All right. So the tangent can also be used or created by finding the slope of the hypotenuse. We'll talk about the unit circle in a little bit, but what we're really looking to do today right here, this is the big idea. Create the trig graphs using the unit circle. All right. Create the trig graphs using the unit circle. And this is really pretty easy today. Now, one thing I'm going to tell you is this. I've gone ahead and looked at pretty much one, or given you the graphs already here. These are what they're going to be, and I'll show you how they come up with them here quickly. But one thing I would like you to do is this. One thing I'd really like you to do is this. Go ahead in here and get an X and Y axis drawn in here better than what I have right now. So on your notes, go ahead and draw all those in quickly, okay? Okay, so you see where it's 0 and you see where it's 0. The horizontal is 0.
On every single one.
And the vertical, yep, do it for every single one of them. Okay, it just is a lot easier to visualize. It didn't show up very well when I graphed these or cut these out, but oops. Okay, got all the X, Y axes in there? All right. So guys, what I'm going to tell you right here is this. These are the graphs that they're going to come up with, and we're going to show you how to get these values real quickly here. But guys, take a look at, if you go to your special angles chart, first of all, what function am I even talking about right up here? Looks like the sine function, okay? Guys, in that right there, look at your special angles chart and tell me what the sine of pi over 2 radians is. 1, isn't it? Okay. Look at this graph right here. When I get to pi over 2 radians right here, what's my graph go up to for the sine function? What value?
1.
1. It's right here, isn't it? Okay. Check out the value of the sine at pi radians. What do you get?
0.
0. Isn't that pi radians 0 right here? Okay, and then how about 3 pi over 2? What's the sine of 3 pi over 2 according to your special values chart? -1. So they get that value right there. So at 3 pi over 2, the sine of 3 pi over 2 when I plug that in for x is what value? Well, -1. What do you think without even looking at the chart, looking at the graph here, what do you think the sine of 2 pi is going to be? 0. Okay, so do you understand how these graphs are formed? They basically are just coming from those angles, those special angles, and they're plotted the value, and that's how the points are given. Okay. So this is after, this is all one revolution right in here, isn't it, gang? Isn't that one revolution of the unit circle, 2 pi radians? And then when we start repeating revolutions around a circle, don't we start starting like a cycle or a repetitive type of values? So this graph right here, the word they use is called sinusoidal. Sinusoidal meaning it just repeats its frequency or repeats its wave. It's like a repeating frequency. Okay? And we'll talk about stuff like that as we progress through this chapter, but I'm not going to get too specific about these graphs. These are the general graphs right here. Okay? One thing I want to tell you is this. I always get kind of scared when I start talking about this stuff, but jump down to like the tangent function right here, guys. Go on to your special angles chart for me and look up the tangent of, this is a goofy graph. It kind of goes like this sideways and then there's vertical lines. You know what you call those vertical lines? They're a line, yeah. You guys ever heard of asymptotes?
Yeah.
Ever heard of functional asymptotes? When I get really mad in math class, I say, if you don't knock it off, I'm going to kick your functional asymptote. Kick your functional asymptote!
And you're gonna kick my line?
Better than kicking your dog, isn't it?
Yeah.
Derek's looking at me like, this guy's freaking crazy. And he's right. Yeah, these are called asymptotes. Check it out, guys. Just go to your chart on the tangent function that I'm looking at right here. Go to the tangent of pi over 2 and tell me what you get on your special angles chart. What's it say? Does it say infinity?
Oh, tangent. Yeah.
Tangent pi over 2, does it say infinity?
Yeah.
What that means is this, there's no value to be able to tell you what it's equal to. This line is going to keep going all the way up, but it's never going to cross this line right here. So what this really means is this. These are basically parts right here where the function is undefined. If I could, like this, do this for me. What's the sine value at pi over 2? Isn't it 1?
Yeah.
What's the cosine value at pi over 2? Isn't that like 1 divided by 0? So everywhere in that chart where you have infinity, that just is really implying division by 0, which is undefined. So anytime you see these vertical lines like this, that's going to be where the function is undefined. We cannot get a value there because we're dividing by what? 0. Okay. So what graph is this right here? Cosecant. So if I ask you the question, what's the cosecant of pi over 2 from this graph, what would you tell me? 1. Okay, I'm not going to go into this much more. You can read these graphs. Those are the general shapes of them. Okay. Any questions about that? Any questions about that? Okay. Next page then. One thing I'm going to do is come back to that graph and talk about some repetition, how often these graphs repeat themselves. Right here it talks about graphing the function of the cosine of theta from 0 to 270 degrees. Okay. What is 270 degrees equivalency in radians, kids?
3 pi over 2.
3 pi over 2. Now one thing I wanted to show you is this. I think that some of the graphing and some of the questions that can be answered come from decimals. And this is what I want to show you today. Okay. Jump into decimals. First of all, on those graphs you were dealing with radians to begin with, right? All of a sudden now they're saying, hey, let's use what now? Degrees. So to give you an idea of what's going on here, I could jump back to this right here and say, well, this is what the cosine graph is going to look like right here. Let's start up here. go like this, but I want you to get used to what they look like. I'm going to have you just do this on the computer and then answer your questions on your assignment. So here's how this is going to look. First of all, what are we trying to graph there in that first example? So was it the cosine of theta?
Yeah.
Okay, here's how I want this to work today. First of all, this time now, instead of talking about radians, we are now talking about what? Degrees. So in your settings up here, in your settings, what are you going to want to come down here and click? Degrees. Okay. Click that. Now, the next thing I'm going to tell you to do is to change the axis, all right? And this is pretty easily done right here. You can change that value. What's the lowest x value that they said? Or in other words, theta, what they used was theta, right? Theta is just like an x, so what's the lowest angle I'm going to use there? 0 degrees. So I'm going to change that to 0. And what was the highest value? 270. Okay, now do you see this part that says step right here? I would say let's step off and listen. Unit circle is broken up into quadrants, isn't it? You guys agree with that? So I would say let's step off every 90 degrees. Isn't every 90 degrees a change of quadrants? Okay, so let's step off by 90 degrees. Okay. And then talk to me about cosine values, guys. Cosine values, what do they range from? What's the lowest a cosine usually gets to?
-1
And what's the highest it gets to?
1.
Positive 1. So down here for the y values, I might change those y values to -1 up to what? Up to positive 1. And how about a step of 1? Okay. So what are we going to type in here then, guys? What's our function that we're really trying to graph now? Y equals what? You hit y equals and then hit the functions button up here. See the functions that pop up for you? What do I want?
Cosine.
Cosine. Anywhere where there's a theta, I can always use an x.
Beautiful.
Okay, so you've graphed part of the graph. You're just basically saying, here's my parameters. I want to start at 0 degrees. At 0 degrees, what's the sine value, or I'm sorry, cosine value, guys?
1.
Okay. Nice thing about this is this. You can kind of, I love this calculator because wouldn't 45 degrees be right about in here, halfway? You could go right up here and kind of click on the line right there, and it would say, oh my gosh, 45 degrees, you could kind of click right on the line to get to your degree and just follow it around. See how it kicks those values out to you? So if I wanted the cosine 65 degrees on this here, just click to get to 65. Maybe.
0.4226.
Yeah, it's pretty neat, isn't it? You just follow it around, gives you all the points. You guys like that?
That's
Pretty sweet, isn't it?
yeah.
Right? So I guess what I'd ask you to do to get comfortable with this calculator, the next thing that it says to graph there is graph the cotangent of -90 to 90. Now, one thing I'll tell you is this. When I go back to my graphs here for cotangent, does the cotangent graph have functional asymptotes or not? Or are there vertical lines present in here? It does, okay? So what I would do is this. I would go from, let's go from maybe, let's go to 25 on that for your verticals. Okay, positive 25, negative 25, and step off by, I don't really want to do that. Let's just go by positive 5 and negative 5. Is that fair like they did here? Is that okay? Okay. So what are we typing in here then, guys, for our window on the next one that we want to graph? Okay, let's get our window fixed right up here. So come up to settings. We're going to graph, what was it, the cotangent of x, was that right? Or theta, whatever, interchangeable. We want the cotangent of x. And what was the window that they want us to show?
0 to 90.
0 to 90?
-90 to 90.
So negative 90 degrees to positive 90 degrees. And again, when we're talking degrees, what's a good stepping stone when we change of quadrants?
No.
If you're in radians, what would be a good step? Let's see, 0 degrees here. What's 90 degrees in radians? Pi over 2. So if you had to be in radians, a good step would be pi over 2. But since we're in degrees on this one right here, let's change this. What's the, click on that x right there. Negative 90. What's the positive here?
90.
And what would be a good step in degrees? 90. And then the y-axis, since we have functional asymptotes here, or vertical asymptotes, if you will, the y-axis I think we should change to -5. Heck, let's just go -10. What the heck? Let's go -10 to +10. And let's step off by 1 and see what that looks like. It's kind of goofy, isn't it?
Yeah, please do
I don't like that very well.
that. You're still on cosine though.
Oh, this is very true. Very true. I need to change this to what here? Thank you, Caitlin. Yeah, we want the cotangent of x, don't we? Oh, where is cotangent?
Bottom left.
Bottom left. There it is.
Yeah, you might want to.
Let's go by 5s on this. I think 5s might be a little better, don't you?
How far out were you?
I'm out to 4,500.
Okay. So another thing you could maybe do here, gang, is this. Where does it appear the vertical asymptote's going to be for this? This kind of mirrors itself, doesn't it?
Yep.
Where does it appear the vertical asymptote's going to be on this? It'll look like the y-axis right here. Okay. So if I ask you to sketch graphs, you understand how to change the windows in there. I'm not really going to say sketch the graph. What I want to tell you to do is use this tool to answer the questions that they want you to do. Rather than graphing it and answer the questions, where do I want you to put your graphs at? In decimals. Okay. And again, so suppose I wanted, I don't know, wouldn't 45 degrees be right here, gang? I want the cotangent of -45 degrees. What is it?
-1.
Pretty cool, huh? Okay. Understand how to use this then? And again, you can zoom in, zoom out. If you keep zooming out a little bit,
That
you know,
becomes red.
it just becomes more and more.
A red ball.
Yeah.
Okay, and again, what you could end up doing is saying, well, if I screenshot this, watch what I can do. You know, the part we're really concerned about is right here, between -90 and +90, isn't it? From here, whoops. I'm really concerned about -90 to, hey, what's going on here? That's not cool. I want from here. Okay, this is obviously not working for me. And that's okay. Okay. But that's what you would end up with, okay? All right. Questions about how to use that at all? All right, let's see where we're at, notes-wise. So, if they say anything about graphing stuff within a window, where are you going? Yes. Okay. The part that gets kind of confusing is right here. The part that's kind of confusing is going to be this part. It says, by looking at the graphs of trig functions, we can have a great conversation about what it means to have domain and range. Okay. When I talk about domain and range, what values of the domain, I should say this, do the domain numbers belong to x values or y values? We're guessing. Okay. Acronym time. Don't take this out of context. Guy's name is this. Remember that name forever for the rest of your life. Roy Dix. Okay? Range is really an output, which is a y value. Domain is an input, which is really an x value. If you can remember that name, you'll never ever confuse that ever again. Okay? Okay? Roy Dix. When it comes to domain and range, what are you going to remember?
So it's range.
Range is an output value or a y value. They're all used interchangeably. So if I had this point right here, like say, I don't know, listen to my questions. When I input 3, my output is 7. Let me ask you this question. On that point, what's the domain?
3,
3. What's the output?
7,
7. What's the x value?
3,
3. What's the range?
7.
Make sense? See how it all ties? These are all, this is the range value, or it would be considered, I'm sorry, this would, I have it kind of backwards, but, so if we were, if this guy was applying for a job, this is how you put it in. First, last name first, first name last. The domain is an input value, which is an x value, okay? The range is an output value, which is a y value. Remember that? All right. So why do we care about these functions? Well, here's the deal. When we start talking about the domain and range, here's what I'm going to get at. Guys, the domain. What functions, what values of x does this cover if it just keeps going on like this?
1 and negative.
The x values. What x values are being covered?
1 and
This is going to go on forever to the left, isn't it?
Oh.
Domain, the x values. What values of x would be covered here, left to right? This is going to go on forever to the right, isn't it? This is going to go on forever to the left. So I would say right here for this function, the domain is, write it down, all real numbers, right? All real numbers is going to go on forever, isn't it? So doesn't this graph just continue to go left and right? Are there any interruptions in the graph anywhere? When I talk about interruptions, doesn't that occur where you have asymptotes here?
Yes.
Okay. So the domain is going to be the set of all real numbers. How about the range? How far up and down do we stretch it? In other words, what y values are covered?
1.
So the range would be, what's the lowest value you can have?
Negative 1.
So it can be down to -1. We write it like this. And what's the highest it can be? What's the highest it can be?
1.
Positive 1. So I write it like this. I say y has got to be greater than or equal to -1 when I write it this way, right? Or it has to be less than or equal to +1. What that really says is my y values, or your range, if you will, goes from -1 up to what? -1 up to +1. Okay. Cosine, domain. Tell me what the domain is.
All real numbers.
All real numbers. It stretches from left to right. It's going to continue to go left, and it's going to continue to go right. Okay. So the domain is going to be all real numbers. How about the range on this puppy? So what's true about the domain and range for sine and cosine?
They're the same.
Exactly the same. Right? Exactly the same. So I would say -1, less than or equal to y, less than or equal to 1. Okay. Well, we start running troubles down here then. Start running troubles down here. Let me get rid of that. I just said Okay, first of all, talk to me about the range of this right here. Are there any x values that do not work, or would there be any situations where the function is undefined?
For tangent?
Yeah.
Yeah.
Happens at, let's see, looks like it happens right here, doesn't it? -π/2. Happens at π/2. Happens at,
Whenever it's over 2.
yeah, when it's over, what is π/2 right here as an angle?
90.
What is 3π/2 as an angle? 270. Talk to me about that interval from 90 to 270. How much
Every
distance
90
there?
degrees.
From 90 up to 270.
Oh, 180.
So what I'm going to say here is this. My domain is the following. And this is going to be really goofy. It's going to be all reals. Can I spell that? I just totally... Reeks. All reals where... Now watch what I write here. It's going to be all reals where x cannot equal... That's a symbol for cannot equal. Okay, what was the first positive angle where we had a vertical asymptote? What was this angle right here? 90 degrees. This angle gave us a vertical asymptote. So x cannot equal 90 degrees. And then what was the interval up to the next vertical asymptote? We went from 90 up to 270 where the next vertical asymptote lies. How many degrees is that? 180. So I write this as where x cannot equal 90 degrees plus or minus 180k. All right, the k just represents a positive or a negative integer, meaning if I took 180 times 7, whatever that number was, if I took 90 plus 180 times 7, all right? So you might say something like this if you want to shorten it up. The domain can be all reals such that x, you might want to write x cannot equal 90 plus or minus what, guys? 180k. Now 90 plus or minus 180k means the first one occurs at 90, and then every 180 degrees to the right of it or every 180 degrees to the left of it, you have a vertical asymptote. Okay? Make sense? How about the range on this? How far up, how far down? Okay, so the range on this is going to be all what? Range is just going to be the reals, isn't it? Continues to move up, continues to move down. Any breaks moving up or down? Okay. All right, so since we've kind of got this stuff figured out about the domain, let's finish up for the rest of these functions here. And guys, really what this is saying is this. When I say this plus or minus 180k, there's talking about how often does this repeat. Okay. Well, take a look at this right here. What was the tangent of 0? 0. Tangent of pi, which is 180 degrees, is still what? 0 again. Looks like its values repeat every how many degrees? This one plus or minus 180k really says it repeats itself every 180 degrees. Okay. So maybe I make a note like this right here, and I'm just going to write it right on here. I'm going to say it repeats every 180. This repeats every 180 degrees. Okay, and maybe I should back up to the other ones. Maybe I should back up to the other ones too and talk about how often they repeat. Guys, this is one cycle of the sine function, all the way up, all the way back down. See how the red down would basically map over here? If I took this line and moved it over now, wouldn't that map to right here? So the pattern gets repeated here over and over, and that's just one cycle of it. From 0 up to 2 pi, how many degrees is that? 2 pi radians is the equivalency of 360 degrees. So the sine and cosine actually repeat every 360 degrees. Okay, so stuff starts repeating itself in those two functions every 360 degrees. Okay. Look at this one here, guys. On the cosecant, doesn't this point right here kind of match that point right there? Okay, so if this was the 2 points, all right, going from negative 3 pi over 2 to positive pi over 2, that's going to be 360 degrees again. That's 2 pi radians distance right here. So this one's also going to repeat every 360. So I'll just tell you what they are real quickly. This repeats every 360. If cosecant was every 360, what do you expect secant to be? 360. Hey, think about it. Sine and cosine repeated every 360, right? Aren't cosecant and secant just the reciprocals of those two functions? So it stands to reason that those would also repeat every 360 degrees. Guys buy that? Okay. Well, if tangent was every 180 degrees repetition, what do you think cotangent is going to be then? Yep. So you might want to jot these down. This is good information to have. Repeats every 360. And then the cotangent function is going to repeat every what? Repeat every 180 degrees. Okay, good. So let's get these domain and ranges knocked out of the park, and then we'll finish up with what we need to finish here, and I think we'll have what we need today. Okay. So talk to me about the domains on this one right here. This one here is an asymptote right here. The y-axis is an asymptote. Okay. So talk to me about the domain. How many x's does it have? This could go on forever, right?
Yeah.
What is the first asymptote I get right here, actually?
0.
Right at 0. So the domain x cannot equal 0. X cannot equal 0. And then I'm going to say plus or minus. Every how many degrees does this repeat then for the domain?
No, 180.
Every 180 degrees K. So the x values. X can be anything. It just can't be 0 plus or minus 180 times K. Understand K is a whole number, right? Okay. Can't take 2.5 180 degrees. It's 1 180, 2 180s, 3 180s, 4 180s, 5 180s. You get the picture, right? How about the range on this puppy?
Every 3.
Looks like I've got y values greater than or equal to what here?
1.
Or
Plus,
less than or equal to 1. So the range, we're going to say y is greater than or equal to 1. That's from this point and above all the y values, right? And right here, this is where y is at -1, every point below that, right? So y would also have to be less than or equal to -1. Okay. Hey, cosecant and secant, how do those graphs kind of match up for domain and range?
same.
Kind of same. Doesn't it look like you're for, ooh, careful on the asymptote here. Oh, where's your first functional asymptote? Right of 0, how many degrees is that? 90, isn't it? Okay, so I'm going to say this. I'm going to say for the domain, x cannot equal what, guys? X cannot equal what value? What's
90.
the first asymptote? 90? Plus or minus how many degrees of repetition on asymptotes? 180K. Alright. Maddie, you glad you're not doing this stuff? Man, she's rocking out. She awake?
Yeah.
How about the range?
Same as 1.
Y is greater than or equal to 1. Y is less than or equal to -1, right? Good? Alright, last one here then. I'm going to just tell you this right here. The domain and range are going to be very similar to what we had up here for tangent. Let's go ahead and take care of this. The domain. Where's the first vertical asymptote at for cotangent? Looks like right at 0. So x cannot equal what? And then how many degrees does this repeat itself?
180.
This is getting kind of shoddy. Can you guys read what I'm putting down here? It's kind of hard to read. This says the x cannot equal 0 plus or minus 180 times k. How about your range then for this?
Real numbers.
All reals, right? Okay. Guys, does that idea of Roy Dix help you at all?
Yeah.
Help you remember which way to go? Which is which? Domain is x. Another way to remember is D comes before R in the alphabet. Domain comes before range in a dictionary, just as x would come before y in the alphabet. Another good way to remember it too. Okay. There's a lot of information on this page. Now, to be truthful, this page is pretty much going to be your savior on the assignment, along with the graphing calculator stuff. So let's use what we know right here about all the times it repeats and what the domain and range stuff is for these types of functions to answer the questions that we need to look at here. This is why do we care about the graphs of the trig functions? They help us find values of other trig functions that may not be on unit circles. So for instance, the one thing that I have here is the sine of what? 810 degrees. I can follow a graph out to 810, but we know from our graph that the sine function repeats every how many degrees? 360. So couldn't I back that down into a window where we're talking about 1 revolution on a unit circle? Remember when we did coterminal stuff? Okay. Well, for the sine function, back it down. Subtract the 360. Anybody know where you're at? 450. 450 gonna fit your window on that special angles chart. Back down then another 360. Where you at?
90.
So I'm really looking at the sine of 90, which is what value? You okay with that? Sine of 180. Are we good on sine of 180? Well, yeah, because 180 fits your window right away, doesn't it? What is a sine of 180? 0. How about cosine negative 90? How often does a cosine repeat itself?
Every one.
Every 360.
Every 360 degrees. Add 360 degrees. What have you got? It's really the cosine of 270, right? Which is what value? 0. Okay. Oh, what's true about these two functions right here? They're the same. Okay. Wow, 90 degrees. That fits your window? Let's go scan 90 degrees then according to your chart. 1. Let's see, secant negative 90. Don't like secant negative 90. What do we say about the repetition for the secant function? Every what?
180.
Be every 360, wouldn't it?
Yeah.
So on your chart, this would be the same as the secant of, which is?
Infinity.
So undefined, right? Secant 0 degrees. Check it out.
1.
Okay, and even if I didn't like the special angles chart, couldn't I come back up here and say, well, here's my graph. Here's my secant graph. Secant of 0, what's it appear to be up here? What point would that be? 1. Okay. So it would be 1. Guys, I'm just going to kind of talk to you what this means. It says we can also determine what angles have a specific value. Guys, on your chart, the sine of theta equals negative 1 at what angle? 270. What's this plus 360k mean, man?
It's the revolution. How many
Repeats itself. Sine function repeats itself every how many degrees? 360 degrees. Tangent is undefined at 90 degrees. How often do we say a tangent function repeats itself?
plus 80?
Every 180 degrees, right? So how about the cosine of theta? Where does cosine of theta equal 1 at first?
0.
0 degrees, right? So we would say 0 degrees plus,
9.
how often does the cosine function repeat itself now? Every 360 degrees, right? You okay with that? How about the cosecant of, where's cosecant 0 at? I'm sorry, where's cosecant of theta 1 at? That's what that says.
90.
So 90 degrees plus every, and actually I want to back up on this. I want to change these all to plus or what? Minus, because we could also go backwards as well. So do that.
Well, isn't that what the K means?
That's what the K, I guess the K could be negative. Doesn't matter. I like that. It doesn't. It doesn't matter what you think. The rock says it doesn't matter what you think. Jabroni. Anybody know who the Rock is? Anybody watch the Rock back in his prime? When he was a WWE professional wrestler.
He came back.
Derek, do you watch wrestling?
Hey, he came back.
Huh?
He came back.
Who came back? That WrestleMania was fixed. John Cena should have won that. He did win the second one.
The Undertaker got beat though.
Did you watch that?
Oh, you bet I did. Sam, that is my soap opera, dude. WWE is so my soap opera. I love that stuff. Secant 0. Let's close this down today.
So do you like recorded that? Like,
I'm not that hardcore.
He came at 0.
I used to be. I used to be.
0.
There is no 0.
Secant 0 is undefined then, right? So we'll say undefined. Wait. We'll just say it's undefined then, right? Are you sure on that? Yeah,
Secant of 0, there is no
doesn't
0.
exist, right?
Hey, do you know who lost their sponsorship
Okay.
today?
Who?
Janet Patrick with GoDaddy. They're pulling it
Going
out.
after this year.
Seriously?
Wait, this chart says it's equal to 1.
Does it?
Yeah.
Secant of 0.
Secant theta equals 0, not the degrees.
So go down to secant, do you see 0?
Yeah.
Okay, are we good?
Yep.
Okay, so you just had the X and Y mixed up. Okay, let me get you a short assignment on this to get started on. You guys okay with what we did up here today? That second sheet really is going to answer a lot of your questions. Are you guys good on graphing?